Hi, in this video I'm going to discuss about operations on real numbers. Okay, so we have seen in our previous classes and we have also performed operations on natural numbers, whole numbers and integers, and also on rational numbers, and we also performed operations on fractions. But from now on what we will be doing is that we will be handling real numbers. Okay, so we have extended our universe of numbers or our space of numbers. Okay, so now let's first look what happens when we add, subtract, or take multiply or divide to an irrational number with a rational number. Okay, let's first check this case. Okay, let's take an irrational number, square root of 5. Okay, so square root of 5 is an irrational number. Right. Now let's add an irrational number and a rational number. Let's say 2 plus square root of 5. Okay. So we are adding a rational number and an irrational number. So what will be the answer to it? Right? Since this is this number, which is an irrational number, has you know that square root of 5, an irrational number, has non-terminating non-recurring decimal expansion the same is true for the given number. Okay, so it will be the sum of these two numbers, and a rational and an irrational, will also be an irrational. Why? Because this rational number is going to just get added to this to the integral part of this square root, and we know that square root of 5 is an irrational number, and it has a non-terminating and a non-recurring decimal expansion. Okay, so this will also be irrational. Now let us see what happens when we multiply a rational number by an irrational number or with an irrational number. Let's say it is 3 times square root of 5. Square root of 5 is like something, square root of 5 equals 2.236 and so on. So 3 times or thrice of square root of 5 will be 3 times 2 is 6.236. So this will just be, sorry, that is not like that. You have to multiply everything. So it will be something this much. Okay, 3 times square root of 5. Now this is the decimal expansion which is non-terminating, so this decimal expansion will also be non-terminating. Okay, so this also becomes an irrational number. Yeah. Now let's check what happens when we subtract a rational and an irrational. Okay. So let's take an irrational number. Let's say this is square root of 3 minus 2. What do you expect it to be? This will also be irrational. And square root of 3 is, let's say it is about 1.7 and something. Yeah, it's almost 1.7, so on. So yeah, it will be negative. Yep, this will be a negative rational number, but that's okay. Irrational number, yeah. So irrationals can be negative too. That's not, and that should not be surprising. And also, if you like divide a rational by an irrational, you get an irrational. So the result of the conclusion is that whenever you combine a rational number or an irrational number with a rational number, you always get a irrational number. Okay. So if it's like if you put or if you mix an irrational number to a rational number, it becomes irrational. But what happens when we add, subtract, or divide or multiply two irrationals? If you add, subtract, multiply, or divide two irrationals, right? So the result you will get, the result may or may not be irrational. Yeah, so this is these were some points to remember, to take note of. And then now we turn our attention to something called to representing real numbers on the number line. Any real number, it be it square root of 3, square root of 5, or square root of, let's say, 9.6, whatever. We will learn to represent these numbers. Okay. Yeah, one thing I would like to mention here is that, let's say let a greater than 0 be a real number. Okay. Then if we say square root of a equals b, it means that b squared equals a, and b is greater than 0, okay? And b is greater than 0. So we are taking square root. We are taking square root of a real number a, which is positive, okay? Remember that it must be positive inside this radical symbol. This real number should be positive. You cannot take a square root of minus, let's say 3.4. No, that is not defined. We will look into it later. But for now, remember that the condition is this, that a is a positive real number. Greater than 0 be a real number. Then square root of a equals b means, or you could say that square root of a is some number whose square or the number after getting squared gives you a again, right? It's like, let's say square root of a is, if it is 2, let's say square root of a is 2, then this a is the square of 2, right? Then this a is, right? That's what it means. Yeah. Now we will learn to how we can represent any real number on the number line. Let's say we have to represent x equals 2.5. Then 2.5. What will this be, right? How much is this? 2.5. Finding square root of 2.5 geometrically. First we will find this. Find square root of 2.5 geometrically. Yeah. That is the question. So what do? We first draw a line, yeah, of this much length. So this is of 2.5, and we let's name this line segment as AB. Okay, and this is 2.5 units. The length of this AB is 2.5 units. Then we extend this line segment by 1 unit, and let's say this is the point C. Okay, this is the method to, you know, to get this value geometrically. Then what we do is that we find, so it is like 2.5 plus 1. We find this, the center of this line segment AC. So it will be somewhere, let's say, right? And mark this and call it O. Then taking OC as a radius, we draw a semicircle. Yeah. So now this OC, or you could say OA, now we take into consideration this whole line segment, okay? So this becomes our radius. OC is the radius. Right? So, and then we draw a perpendicular to AC, which goes through B, right? And intersects this semicircle at say D. Yeah, we have taken we have used these alphabets A, B, C, and that's D. Now this length BD represents square root of 2.5. That's amazing, right? And that is amazing. So this is how you find square root of x for any real number x greater than 0. Positive real number, right? And let me show you why does it work. Okay, let's do that. So, you first, let's say square root of x. Geometrically, finding it geometrically. So we draw a line segment, call it x, and here is A and here is B. Then we extend this line segment by 1 unit and we mark this point as C. And then we find the midpoint, right? Then we find the midpoint of AC and let's call it O. Why do we use O? O also resembles 0, and O is also the the initial letter of origin. And origin, as you would look in the upcoming chapter, that it is a concept, is a term related to coordinate geometry, right? So this is O. So this midpoint, now taking this O from O as the center and OC as the radius, we draw a semicircle. Okay, and then we draw a perpendicular to AC through B. Yeah, like this. And this perpendicular, this length, gives you square root of x. Let's solve this T. Why is it so? So let's look at this triangle. Triangle OBD, right? Now this triangle OBD, as you can see, is a right angle triangle. Why is it a right angle triangle? Because we have clearly drawn this perpendicular to AC, and perpendicular is makes an angle of 90 degrees with another line, or with another line segment, right? Since this is a right angle triangle, we can use the Pythagoras theorem effectively to prove why this length, this BD, is square root of x, right? So first look, so we need this OB, right? This OB distance and this OD. So yeah, OD equals, this is the radius, so is OC and OA. OC equals OA. So these are the radii, right? This is OD This is one radius, this is another radius, and this is the third one. So these all are equal, right? We know that radii are equal in the same circle. So all these are equal to how much are they? Oh, they are equal to, yes. So this is OC, and this was, yeah. So it's right that this was x, and this was 1, and this was, midpoint. So this is x plus 1 half divided by 2. This is x plus 1, and this is the midpoint. So this length is half of AC. Now AC is x plus 1, so half of AC is this. Okay. Then we need to find OB, right? We need the length of OB. How much is OB? So OB equals, this OB equals AB minus OA. Yep. AB, if you subtract OA from AB, you get OB. So this is, AB is x, and OA is minus OA equals this, x plus 1 upon 2. So it comes out to be, it will be 2x minus x, this is x minus 1, So OB equals x minus 1 upon 2. So we have got OD, we have OB. So we only need BD. So now we will use Pythagoras theorem to get BD. Okay, so let me do it somewhere here. By Pythagoras theorem, PT means Pythagoras theorem here. We know that BD equals to square root of, we are directly using this formula. BD equals to the square root of OD squared minus OB squared, right? So what is OD? OD is x plus 1 upon 2 whole squared. So let me erase something. Let me erase this line. So OD is this, x plus 1 upon 2 whole squared minus OB. OB is x minus 1 upon 2 whole squared. And then we take the square root of this expression. So x plus 1 upon 2 whole squared equals to x plus 1. So we can separate, we can calculate the squares of these two, the numerator and denominator separately. So this will become x plus 1 whole squared, which is x squared plus 2x plus 1 upon 4. And then this square distributes to denominator as well. So this becomes 4, and then minus x squared minus 2ab plus 1. So it will be minus 1, and this becomes minus. This will become plus, and this will become minus. Minus 1 upon 4. And take the square root of this whole expression. X squared gets cancelled with x squared. Now this should not have been like that. I have made a mistake. So this is x squared minus x squared minus 2ab minus 1 is plus. Oh no, it is not. I haven't made a mistake. So x squared, so what it becomes is that x squared gets cancelled because the denominators are the same. So x squared gets cancelled. 2x plus 2x becomes 4x plus 1 minus 1 gets cancelled. And then we can just write it as plus. We should also change this sign because of the and this becomes minus. Minus plus minus. 4x upon 4. Now it turns out to be equal to, I have drawn this symbol a little more long, so this becomes square root of x. So as you can see that BD equals square root of x. So by applying this Pythagoras theorem, in this case, we can prove that y bd equals square root of x. Okay. So this is a good way to visualize the square root of a real number geometrically. And if you want to plot or represent this number on a number line, you take this O as 0, or this O origin or the center coincides with 0, and then it becomes and this, yeah, no, not like that, it will just mess up. This B coincides with 0, and this C becomes 1, and so on, right? So this is how your number line starts. And then you take the length of BD, and from here, this is 0, you take this length and you just intersect this number line somewhere here, and this is how you get the representation of this number. Now let's solve some questions which follow after this section. The first question asks us to classify the following numbers, to classify a bunch of numbers as irrational and irrational. The first number is this: 2 minus square root of 5. What type of number is it? Is this rational or irrational? Look at this difference. So square root of 5 is irrational, you know it, right? And 2 is rational. When you mix a rational with an irrational, you always get irrational, right? A rational with an irrational gives you irrational. And the second one is this: 3 plus square root of 23 minus square root of 23. So first we simplify it, okay? So what do we get? On simplifying this expression, we get 3. So this is rational. This is clearly rational. And the third one is, because this positive 23, square root of 23 gets cancelled by this. 2 times square root of 7 upon 7 times square root of 7. Now square root of 7 cancelled by square root of 7 in the denominator, and we get 2 upon 7, which is rational. So this is rational, and this is also rational. And the fourth one, this is 1 upon square root of 2. So yeah, this is irrational. Right away you can tell this is irrational. Why this is irrational? Because in the numerator you have a rational number, which is 1, and in the denominator you have an irrational number. So whenever you combine a rational and an irrational, you always get an irrational number, okay? If it is in the simplified, in the reduced form, and if it needs more simplification, then you should do that first, and then conclude whether it is rational or irrational. Now let's move on to the fifth question. So as you can see this is 2 twice of pi. So pi is an irrational number. So 2 times an irrational is also going to be irrational. Oh yes, now we are here to this question where we have to simplify following expressions. Yeah, so let's simplify them. So the first one says to simplify this expression, which is 3 plus square root of 3 times 2 plus square root of 2. Yeah, so how do we solve this, or how do we simplify this? We use the distributive property to solve this, to simplify this expression. So we distribute this 3 over this expression. So 3 times 2 plus square root of 2, then plus square root of 3 times 2 plus square root of 2. As you can see that this 3 gets distributed to this, or it's like 3 times this, then square root of 3 times this. So now we go one step further. 3 times 2 is 6, and 3 times square root of 2 is thrice of square root of 2, plus this times this is twice of square root of 3, plus square root of 3 times square root of 2, and they will simplify to give square root of 6. And this is 3 times square root of 2, 2 times square root of 3, so they are not going to give you anything better. But yeah, you can, somehow make them, if you want to take common. So this will again become what we have started with. So this is 6 plus 3 times the square root of 2 plus 2 times the square root of 3 plus square root of 6. So we cannot simplify more than this stage. So we have written this expression as the sum of rationals and irrationals. So this is rational, irrational, irrational, and irrational. So one rational number and all the other three terms are irrational. So when you reach at such a stage where you have expressed that expression as the sum of rationals and irrationals, that's enough. And you cannot go further, right? You cannot add any of these, because these three are irrationals and this one is irrational, so you cannot just add them. So, and I also think that it is not possible to write square root of 2 plus square root of 3 as a single rational number. Let's say this is x, where x is an irrational number, because these two have decimal expansions which are non-terminating and non-recurring. So it is not possible to come up with a single number. Okay, so now let's do another one. So the second part of this question says us to simplify this expression, which is 3 plus square root of 3 times 3 minus square root of 3. So if you can remember an identity, so this is a plus b times a minus b. These two terms are the same, right? What is a plus b times a minus b? You know the identity, right? And you have also been given this identity. So this turns out to be a squared minus b squared. Yeah. A squared minus b squared. So you can, without, doing the actual multiplication, you can just write it in this form and take it. So 3 squared, yeah, so this is going to be 9, 3 squared minus b squared. So b is square root of 3, so this will be 3. So this is going to be 6. So yeah, so we simplified it without actually multiplying these two factors. Okay, let it be written. Now the third one. The third one says to simplify this, square root of 5 plus square root of 2 whole squared. You know a plus b squared, right? This identity, you know this identity, a plus b squared. This is a squared plus 2ab plus b squared. So we will effectively use this identity to simplify this expression. So square root of a. So square root of 5 square a plus b whole square. So square root of 5 is 5, right? Plus twice of a b. So 2 times square root of 10. Yeah, 5 times 2 is 10. Then b is squared. So b is square root of 2. So square root of 2 squared becomes 2. So 5 plus 2 is 7. 7 plus 2 times square root of 10. Now this is irrational. 2 times square root of 10. Square root of 10 is irrational, and multiplying a rational with an irrational gives you irrational. So this is an irrational number and this is a rational number. So we have written or expressed this expression as the sum of a rational and an irrational. Okay, so this is the simplified version of this expression. And this helps while if you write the simplified form of an expression, it helps, oh sorry, not that, of this. So it becomes, or it is easier for us to, make sense of this number rather than this. You can say that 7 plus, so whatever is this greater than 7, right? And this, first of all, you should know what is the square root of 10. Then you can make a better estimate of it. Okay, so now we will simplify the fourth one. Square root of 5 minus square root of 2 times square root of 5 plus 2. So yeah, square root of 2, yeah. So a minus b, a plus b, right? So these two factors, when you multiply these two factors, you get what? So here we will use this identity, a minus b times a plus b, and it equals a squared minus b squared. So a squared will be 5 minus b squared is 2, so it is going to be 3. So this is the simplified version, right? Now the third question. It says that pi is defined as the ratio of the circumference of a circle to its diameter. Okay. Now they say that it might seem to you that pi, which is an irrational number, contradicts this fact, right? Contradicts this result. Now here it seems to us that c upon d is going to be a rational number, right? But in practicality, what happens is that when we measure a length, right? When we measure length of a side or line, we get an approximate value, or an approximate rational number, right? So we do not get an irrational number. Whenever you measure, let's say this is 3.7, 3.8, it's not like 3.81, 811, 8111. You do not get a number like this. So that's why it seems to us that this is rational. Otherwise, either the c is, you know this, right? If pi is irrational, then as per the fact that we saw, either c must be irrational or d, right? One of these needs to be irrational if pi is irrational, because we know that the quotient of a rational number with an irrational number is an irrational number. So either of these two must be rational. But while measuring this, in reality, we do not get an irrational number. So that's why we do not realize that this is an irrational number. Yeah. So that's why. So there is no contradiction, right? Now let's do this fourth one. It says to us to represent square root of 9.3 square root of 9.3. We have to represent this number on the number line. So how would we do that? First, we will find this number geometrically, as we did in the example. We draw a line segment of length of the same length given here, 9.3, right? Then let's name these 2 points as A, B, and then we extend this by 1 unit and let's call it C. Okay. Then we take AC, the entire line segment and find the midpoint of it and take it as the center, and then this being a center and OC being radius, we draw a semicircle. That's simple. Yeah, this method is simple. So there's nothing much to worry about it. Just look at it, how it happens, and then yeah, use it. The more you use it, use a concept, apply a concept, the more you the more comfortable you become. So this OC is radius, right? Then we draw a perpendicular, and this perpendicular, the perpendicular which we are about to draw, is that value, right? The length of that perpendicular gives us what we intended to find. We draw, and that passes through B, passes through this point. And wherever this perpendicular intersects the semicircle, let's say this is D. Now this length, this perpendicular, represents the value of the square root of 9.3 of this number, right? Now we can we can move this figure onto a number line where this B coincides with 0 and this C becomes 1, and then you can take, so this is our number line. So B is 0, C is 1, because from B to C this is 1 unit, right? Then you can take this length by that by that divider or by that instrument, and then you just draw the arc here. Let's say this is M. Now this M, this point M, represents the square root of 9.3 on the number line. On the real number line or real line, on the real line, right? So this is how we solve it or represent this. Now let's move to the fifth question. The fifth question says that we have to rationalize the denominators of the following numbers. So we will, through this question, look or understand and learn how do we rationalize the denominators, okay, if they are not in the rational form. And by rationalizing we mean to convert the denominators, if they are not already in the rational in the rational form, into the rational form, right? So yeah, let's solve this. So the first is this one, 1 upon square root of 7. As you can see, the denominator square root of 7 is not a rational number, it is an irrational number. So what do? We multiply it by square root of 7 so that it becomes 7. Since we are multiplying square root of 7 with the denominator, we do the same with the numerator so that the value doesn't change. The expression or the way this expression looks might change, but the value should not change. So we are basically multiplying this expression by, or this value by 1. The square root of 7 upon the square root of 7 is 1, right? So it doesn't change this value. So it becomes square root of 7 upon 7. Now the denominator is is a rational number, right? And now it becomes easier to handle this number, to make sense of this number, as compared to this one. Now the second one, 1 upon square root of 7 minus square root of 6. Now to convert this into the rational number, to convert this denominator into a rational number, what do is that we will use an identity which is a minus b times a plus b, or you could say that the square root of a plus b is like this, yeah, so that we get a minus b. So if it is the square root of a minus the square root of b, you just multiply by square root of a plus the square root of b. So square root of a So this is square root of 7. So we will multiply by square root of 7 plus square root of 6, and the same on the top as well. Yeah. So it becomes square root of 7 plus square root of 6. But here what do we get? Is 7 minus 6 is 1. So it is basically square root of 7 plus square root of 6. So the denominator has almost vanished. So we have used an identity, and those identities are given in your textbook. Okay. Now let's move to the next one. It says to rationalize this denominator, 1 upon square root of 5 plus square root of 2. So this is, again, we will use the same identity which we used in the second sub question. Square root of a plus square root of b, we multiplied by square root of a minus square root of b, so that we get a minus b, right? So we will multiply by square root of 5 minus square root of 2 and square root of 5 minus square root of 2, and we get here square root of 5 minus square root of 2 upon 3. So we have rationalized the denominator, and it has become 3. And the last one of this part is this one. 1 upon square root of 7 minus 2. Right, so this is square root of a minus b. So we also have an identity for this, and so what you do is that you take the square root of a plus b. Instead of remembering and mugging those identities up, it's basically you just remember one identity, and that is a plus b times a minus b equals a squared minus b squared. What do we want here? We want somehow that this gets squared, right? This gets squared. That's what we want. So we multiply it by square root of 7 plus 2, and the same in the denominator, just 2. So this comes out to be square root of 7 plus 2, and this will get squared. So this is 7 and minus b, so this is 4. So it becomes square root of 7 plus 2 upon 3. Yeah. So yeah, we rationalize the denominator. These were the questions in exercise 1.5, and in the next video we will solve exercise 1.6, where we will learn about the laws of exponents. Now, from now on, we have come across these real numbers. So our scope of numbers have increased, and we have extended it purposefully. So we will apply and perform the operations on real numbers, and also know the laws regarding real numbers. Okay, so you have to keep this aspect in mind, that we are not only dealing with natural numbers, integers, but now we have included and got irrationals as well into our collection of numbers. So we will gradually develop this feeling and this understanding of rational numbers, and we will be comfortable in handling these numbers and making sense of these numbers as well. So yeah, see you in the next video. Thanks, take care.